And as usual, for finding the input impedance, we will be applying KVL at the input side. So apply KVL at the input side. The total applied voltage Vs will be equal to Vi plus Vf. So see here, Vs equal to Vi plus Vf. And you know Vi is the voltage across Ri. Current flowing through Ri is Ii. So Vi equal to Ii into Ri. So Vs equal to Ii into Ri plus Vf. And what is Vf from the expression for this feedback voltage? It is beta into I naught. So Vs equal to Ii into Ri plus beta into V naught. Beta into I naught. See, we have this term Ia in the first term. So Vs by Ia is Rif. But in second term, there is no Ia. So I need to bring this Ia in the second term. For that, I need to find what is my I naught. So I'm going to find what is I naught. Where is I naught flowing? I naught is flowing in the output side. The total current is Gm into Vi, and I want the current flowing through RL. So I have to apply current division technique. Total current into opposite resistance divided by opposite resistance plus that resistance. So I naught equal to total current is Gm into Vi into opposite. To find the opposite resistance, you have to hide this resistance across which you are measuring your current. So hide this RL. Whatever is remaining is your opposite resistance. So GMVI is the current, total current into opposite resistance divided by opposite resistance plus that resistance. So GMVI into R naught by R naught plus RL. I am writing this GM into R naught by R naught plus RS as G capital M, just for simplification. So I'm writing this G small m V into R naught by R naught plus RL as G capital M, where G capital M equal to this expression, Gm into R naught by R naught plus R. So substitute this value of I naught in this equation. Okay, substitute the value of I naught in the derived KVL equation. What we get, Vs equal to this term we already have, Ia into Ra plus beta into I naught. I naught, you know, it is Gm into Ii into Ri. So from these two terms, I can take Ii into Ri as common. So Ii into Ri, if I take it as common, it will be Ii Ri into 1 plus beta into G capital M. So divide by Ii on both sides. So Vs by Ii will be equal to Ri into 1 plus beta Gm. You know Vs by Ii is Rif. So Rif equal to Ri into 1 plus beta Gm. So whenever you know this Ri is multiplied by a big term, so the input resistance with feedback is going to increase a lot. It is going to be increasing. So there are two values of Gm here, G small m and G capital M. See, G small m is the actual trans conductance without feedback, and G capital M will be considering your load. You see the expression for G capital M, you will be always having RL. So in the G capital expression, if you put RL equal to 0, you will get back G small m. So G small m is always the trans conductance without feedback, without load. It is the trans conductance of your amplifier alone. That is why we inside the dotted line we use G small m. Outside this dotted line we use G capital M, because G capital M will consider the effect of load resistance RL also. So that is what is very clearly given here. You see G small m represents short circuit trans conductance without the feedback, without the load. So it is plainly only because of the amplifier. G capital M is the trans conductance when you consider RL and feedback. So G capital M is for the load. And in G capital M, if you put RL equal to 0, you will be getting G small m. That we have found out in this expression. Put RL equal to 0. So Gm into R naught by R naught will get cancelled. So G capital M will be equal to G small m. Okay, so in the expression for G capital M, if I put RL equal to 0, I call it as G small m. And you should clearly know what is the significance of G small m and G capital M. You should know what each notation denotes. So this is going to be, we have proved that for current series feedback, the input, we know that the input resistance after feedback is going to increase. So we have proved in circuit wise that RIF equal to Ri into 1 plus beta Gm. So which means that my input resistance after feedback is going to increase enormously by this factor 1 plus beta into Gm. Now I need to find what is the output resistance. For output resistance, first thing what I should do, I should disconnect my load and I should apply a sample voltage capital V across the load. This procedure is same. See, previously also we did the same thing, right? So RL is disconnected, which means I'm open circuiting RL and I am going to apply an voltage source V and I'm going to find out what is the current because of this voltage source V. So that V by I is going to be R naught F and I'll be short circuiting my voltage source. So Vs will be made 0. So these settings, already we have seen in voltage series feedback itself. So since it is voltage source, we are making it a short circuit. If it is current source, means we'll be opening it. Okay. So the settings are very clear. Remove the load, apply an external voltage at the output side. See, usually input side only has the external voltage, but since if I want to find the output resistance, only if I apply an input at the output side, I will know how much current is being supplied, right? So that ratio is going to be my output resistance. So things are very simple. Remove your load, apply an external voltage V, and you short circuit your input Vs equal to 0. And now